Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at what's the big idea, where we explore calculus on the first day of class using TI Technology. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough to teach, tough to learn concepts accessible to all my students. Tonight we're really lucky to be joined by our two panelists, Dennis Wilson and Tony Record. For the last 24 years, Dennis has been teaching at Landmark Christian School in Fairborn, Georgia. Since becoming a member of the mathematics faculty back in 2001, he's taught every level of math offered at Landmark, from 5th grade to multivariable calculus 2. Dennis is passionate about teaching with technology to help his students learn math using multiple representations. He's served as an AP reader for calculus for the past 5 years and is currently serving as the president of the Georgia Association of Advanced Placement Math Teachers. Dennis, we're excited to have you with us tonight.
Thanks, Mike. I'm excited to be here. It's a great opportunity to get together with so many math educators.
And Tony has been a teacher at Avon High School, a western suburb of Indianapolis, for the past 30 years. For the past 12 years, Tony has primarily taught AP Calculus and has worked to build his school's AP Calculus program to nearly 300 students. In addition to being a T-Cube regional instructor, Tony is an active consultant with both the National Math and Science Initiative as well as the College Board, having trained teachers and worked with students in 27 states. He lives in Avon, Indiana with his wife and 2 teenage children. And in his spare time, he loves to play guitar and is active with the theater. Tony, it's great to have you with us.
Thank you very much, Michael, and hello, everybody. It's such a pleasure to be with you all this evening, and it's great to kind of get together and start talking about the new and possibly different school year that we all have in front of us. Thank you very much.
Absolutely. I know that Tony reminded me whenever we first got on today that Tony starts school tomorrow, so some of you may be in that similar boat starting very soon. We're expecting a large crowd, so your audio is muted. Feel free to send Dennis or Tony any questions using the Q&A window on the right side of your screen. We'll also be using the chat window tonight to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the event. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the very top of the WebEx menu and choose Audio Broadcast. At this point, Dennis is going to discuss our agenda.
So tonight we're going to do welcome introductions, which we have just done. We're going to look at the mathematical practices and the big ideas from the course exam description for the AP Calculus course. We're going to look at a first day activity involving regular polygons. We're going to look at properties of limits and the limits of composite functions, and then do a little exploration of motion to introduce some of the mathematical practices.
Dennis, thanks so much. And Tony is going to walk us through the expected outcomes for tonight.
Yep. First of all, we're going to identify these AP Calculus big ideas and math practices. Primarily, you're going to see, as far as the math practices are concerned, a big emphasis on number one, implementing mathematical processes. And then what I think that the Texas Instrument line of calculators do as well as anything, and that would be math practice 2, allowing us to connect representations. We're going to, like I said, use this technology to explore the big ideas of change, limits, and analysis of functions. This is going to do a really good job of looking at the idea of change and limits. I'm going to focus a little bit more on what we all might be teaching very quickly up front on the first few days of class. That would be limits. And then finally, we're going to reflect on the optimizing the first few days of class to engage students with these big ideas of calculus.
Tony, thanks so much. Dennis, you have control. Feel free to share your screen.
Thanks, Mike. So as we approach the first day of school coming up, there's like so many things that we have on our to-do list for that first day. We might have to like review the syllabus, distribute textbooks, all these administrative tasks. But when I get ready for the first day, I always have one goal in mind that I want to make sure I accomplish with my students. And that goal is for my students to do math. I want them to come to class and know that every day they come to class, we're going to do math. And the first thing sometimes I have to break them of is to let them see what math is not. I want them to learn that it's not following a prescribed set of steps to find an answer. Instead, I want my students to understand that when we do math, we're going to use current knowledge to explore a problem, construct a solution, and discover new ideas. And hopefully take those new ideas into the next day, and we'll use those ideas to explore a new problem, and we'll just keep going through this cycle. And so as we do this early in the year, I try to emphasize those mathematical practices that Tony briefly mentioned that are from the course and exam description. Implementing mathematical processes. I want my students to be able to identify what the problem is and to choose the correct procedures and rules that they'll need to solve it. Connecting representations is a huge one, and I always tell my students that we're going to gnaw on our problems all year, looking at them graphically, numerically, algebraically, and with words. Justification is a big one because I want my students to look at mathematics as a journey and not a destination, as a solution and not an answer, so that they understand that those journeys and those solutions have steps, and we need to have a reason and a rationale behind all those steps we take. And then finally, communication and notation. I want to make them known to my students that no matter what they're thinking and how clear it is, if they cannot communicate it precisely with words and algebraic notation, then it doesn't do them any good. So in 2016, the frameworks were first released, and we had 4 big ideas. They were limits, derivatives, definite integral and fundamental theorem of calculus, and then series. But with the most recent course and exam description, they've been altered. And so these new big ideas, there are 3 of them. There's, change, there's analysis of functions, and there's limits. And at first, I was a bit hesitant about these being the big ideas of calculus, but the more I thought about it, I realized that these are the 3 threads that are woven through every concept that I cover in my calculus class. And then also on the first day, I have certain goals I want to do with my technology. The first is I want to review essential calculator skills. I want to make sure that my students come in with calculator skills that I expect so that I don't have to cover them daily. I want to go ahead and make sure I know what they know and fill in any holes they might have. And then I want to reinforce the calculator as a learning tool. I don't want my students to look at the calculator as simply a computational device that spits out an answer, but I want them to think of it as a vehicle that allows them to explore different concepts, relationships, and their own conjectures. So how do I do that on the first day? Well, what we're going to look at, give me 1 second. Let me reopen my Microsoft Word. So as I reopen my notebook here, whoops, that's the wrong one. Okay, as I reopen the notebook, I just want to point out that you're going to be getting this activity, a link so that you can download it later. And it's PDF or Word document format so that you can edit it and use it however you would like. Okay. Working on it, sorry. Okay, so I want to describe this activity a bit while I wait for it to come up. So basically, what I'm wanting the students to do is to explore the area of a regular polygon that is either inscribed in a circle or circumscribing a circle. And the reason I like this task is that the mathematics is familiar. There's no obscure mathematics in it, and they don't have to try to figure out mathematics that they might have forgotten. Now I just need to get back to where I was in my notes. Sorry. Okay, so I'm not going to go through the mathematics that the students will use to begin this, but what I want to do is I'm going to look at a document on the Nspire, and I'll be using both the TI-84 and the TI-Nspire. Both Tony and I will be using both those platforms this evening. But I want to start out with a pre-made document that I created for the Nspire. And so I think Mike's going to put a link in the window because so that those of you who are 84 users and don't have the teacher software, you can download the free trial. I highly recommend, as an 84 teacher, that you use this software because it allows you to enhance the teaching you do with the 84 because it gives us some really nice visual. And so what our students are going to do is they have a regular polygon here inscribed in a circle, and they're going to split that polygon up into triangles. And you can see there's a shaded triangle there. And so their first task would be to find the area of the shaded triangle. And then once they have the area of the shaded triangle, they're going to multiply it by the number of sides to get the area of the entire polygon. And our hope is that as they do that, they're going to end up with an expression something like this. And so once we have this algebraic equation, for a student entering calculus, it might seem a little different than what they've seen, and they might not fully understand it. So what I want the students to understand is we need to gnaw on this equation. We need to take this algebra and look at it in different ways. And so we're going to use our technology to do that. And so the first thing we're going to do is we want to let our technology fill in a table that would tell us the area of our inscribed regular polygon in a circle of radius 1. And so we've got these different values here. But what I want to do with my students every time before I reach for the calculator is they should reflect on what information the calculator is going to give. What are we expecting? Because that will help inform, first, if our conjecture is right, did we get the right equation? And then also, it will help inform that we're using the calculator right. So this table is representing this picture that we're seeing of different areas for values of n. So in the chat window, what do we expect about the values of the area in our table? What might we expect for the values of the area? What behavior might we expect our students to see? Well, one thing, we know that because our polygon is inscribed inside a circle, we want that those areas to be less than pi. And I see that we want values that are increasing. We can see that the area of the rectangle is increasing if we reflect on the piece of the circle that isn't filled in by the polygon. So we want the area of the polygon to increase. And we want those areas, hopefully, to approach the area of the circle. And since this is a circle of radius 1, we want it to approach pi. So let's look at it on the 84. So I'm going to start off in the SmartView software with just the small screen so that I can see this equation. So if you're an 84 teacher, what are some ways that your student might find the values in this table? What are some ways your student might, coming into your class, try to fill in this table? So depending on your student's knowledge, one thing they might do is they just might decide to come in and do direct entry, substituting directly the value of n with the value that's in the table. So they might do 1/2 of sine of 2 pi divided by, and then the first value in the table is 3 and times 3. So I'm just substituting 3 in for n, and I get this value 1.299. Okay, so I could also, once I've entered that, students might just go back up and grab that value and replace the 3 with the 4. Okay, but that's going to take some time, and what I want to do on that first day is make sure that they use the power of the calculator. So one thing, I can define the function in the y equals page. So I'm going to press y equals, I thought that was cleared out. Sorry. Okay. I'm going to press y equals, and I'm going to put this function in. I'm going to do 1/2 times sine. And now when I'm here in this y equals window, I got to remember that they're functions of x. So I'm going to do 2 pi divided by x, close that parenthesis, set of parentheses, and multiply times x. I'm going to go press second mode to quit and go home. And while this is, yet again, not the quickest way, I want to make sure my students understand that they can evaluate a function from the home screen. So I'm going to press alpha trace to get these y variables, press enter for y1, and then I can put the next value in my table, 5, press enter, or I could do y1 of 6. And so I'm getting these values by entering directly into the function. The next thing I want to do, though, is, and I've seen it in the chat window, is I want to fill in that table. So I'm going to go first and press second graph to take me to the table. And I like going directly here. Let's make it big now that I've got values. Okay. I like to be able to discuss some things that they might not expect, because our table didn't have values for 0, 1, or 2. And we should talk about what does that mean that our table didn't have those values in the context of the problem. But one thing I see about this table is that it increments by 1, and I have values on my table that are increasing by different increments. So instead of going to the table as is, I'm going to set the table differently. So I'm going to press second, window, for table set. And I'm going to go down to this independent variable and move over to ask. And I'll press enter. And now when I go to my table, second graph to go to table, my values of x aren't there. So I'm going to put in some of the other values, so 6. I won't put all of them for the sake of time, but I'll put enough that we get a view of what these values are doing. Notice every time I enter, let me make it big for you, every time I enter in the next value, a new value for x, it tells me that value for y. And what's also nice is that it can give me the full approximation of the calculator is giving if I move over into this window. But this first day, right now, is when I'm trying to plant the seed of how to report an approximation from the calculator. The College Board wants 3 decimal places, truncated or rounded, and I want my students to go ahead and start learning that. And from day 1, that's how we report it. And I tell you, all the way through the first semester, I'm still repeating to the students 3 decimal places, 3 decimal places. And so it's never too early to start. 90, and then I'll put in 180. So now we've got these values, and we can see they are increasing, and they seem to be approaching pi. So they matched our expectation, but if we're going to null on this, we might want to look at the graph of this function. And once again, before I get the calculator to do something, I want the student to think about, from the information we have, what the calculator will give us. So if I were to see these values on a table and I go to my calculator to try to graph them, hopefully my students are going to have an idea in their mind of the shape of the graph. They might not be able to say a horizontal asymptote at pi, but I want to coax that language out of them through discussion. So once they can tell me kind of what the graph would look like, before I go to the graph, I want to hit the window. There are 4 required capabilities for graphing calculator on the AP exam. And I think the first one's the hardest for my students, which is graphing a function in an appropriate window. That phrase, appropriate window, is really difficult for them. But our students, my students, your students, they need to be able to find an appropriate window based on information given. They might have a graph with axes labeled. They need to be able to graph that graph in their calculator in that window. Or they might have a table of numerical values. Or they might just have 4 numerical choices on a multiple choice question that can inform how to set up that window. So I'm going to go to the window, and our table went from 3 to 180. So I'm going to put that as my x values. And my area is always positive, so I'll make y min 0, and y max I will make 180. So we can get that whole behavior we saw in the graph. In the table. So when I press graph, whoops, did something wrong, didn't I? Okay, take a step back. I put 180 for the x max. Let's go with 4. I know that it's going up to pi. Sorry. So 0 to 4 in the y. And so again, like right there, as soon as I saw the picture, I knew it was wrong. And that's why I want my students to think about, even sometimes sketch what they think the graph will look like before they go to the calculator. So when the calculator gives it to them, they understand, wait, something's wrong. A lot of times it's this mode right up here. They'll be in degree mode instead of radian. And so somebody saying it'd be helpful to have the general formula right above it. And I actually have that ability by going to second format, and I can turn on the expressions. Well, no, the expression's on. I don't know. Trace. Yeah, when you press trace, you can get the expression above it. So now that we're tracing, I want to point out that tracing, I trace some values that aren't necessarily good for me. Okay, it doesn't make sense that for my regular polygon to have a non-integer value of size. So connecting the graphical with numerical in the trace window right now isn't the best way for me to do it. So there's some things I could do to change that. And the one I like best is I'm going to press the mode key, and I'm going to go down in the mode from full over to graph table. And when I press enter, what this is going to do is it's going to split my screen from either a full graph or a full table between a graph on the left side and a table on the right. So now I'll press second table. There's my graph, and here's my table. And notice right now, 6 is highlighted in my table, and that's where the x is on the graph. It's at 6, 2.598. And I can push up and down in the table, and it traces those values that I have in the table. This is a great way to make a connection between a table of data and a graph. As a calculus teacher, I like putting the candidate table from an absolute extrema problem right here with just the candidates in. So my students understand that those values they're putting in the table are the ones that are endpoints and critical points, relative extremas and endpoints. So this is a great way to see the behavior and connect those representations. So, have you seen any calculus yet, though? Have you seen any hints of calculus? What are some concepts that you might have seen that a student might need to know in order to do the calculus, that they might see later in the calculus? Okay, so limits is huge. Okay, everybody's saying limits, and limits are a big piece here. They're getting to see that behavior as n goes to infinity of what that graph does. Okay, another thing I really like, and we can see it here with this demonstration. And if you're an 84 user and you're hesitant about trying to get into Nspire, this file is going to be available for download afterwards. And if you download the trial software and install it, all you'd have to do is click on this file and open it, and it does exactly what I'm doing. But what I like is we can see that all these triangles have finite areas. And as I increase the value of n, those finite areas get smaller, and they approach 0. But the number of those triangles is getting bigger, approaching to infinity. And so I have the idea of a product of infinitesimal areas times the infinite number of those pieces, giving me a finite number. And so I can hint right here at that idea of approximating an area by using more and more geometric shapes, and they have an idea of the definite integral. So the next time when I finally come to definite integrals, I can refer back to this idea of polygon that we've seen. So what I usually do with my class is I split half the groups get the inscribed, and then the other half get the circumscribed polygon. Now, I'll tell you up front that the students with the circumscribed polygons frequently mess up the area formula for this one. They have trouble with the idea of that R is actually this piece and being able to try to find what this other piece is in terms of base and height. But it's good that they make mistakes. I want my students to make mistakes. Failure is experience, and what's great is the calculator will refute their mistake just as well as it confirms correct mathematics. So here is the formula for the inscribed area. I'm sorry, the circumscribed area. And just briefly, I want to show one way I might do this on the Nspire. So on the TI-Nspire, I'm going to be in a document page, and I like to make sure that my Nspire students are using documents. The Scratchpad is great for scratch work, but there are so many tools available in the document model. So anytime I explore mathematics, I want to be in a new document. I'm going to press Menu here and open a calculator page. And just like we defined the function on the 84, I can define the function in the Nspire, but I'm not limited to y1 through y0. I can call it anything. So I'm just going to call this f of, and we'll make it n because that's the variable we've been using. I'm going to close that set of parentheses. And when I define a function, I'm just going to press Control, the template key here next to 9. And so our function was tangent. I'll press the trig key, tangent of pi over n, and now close the parentheses, times n. And when I press enter, the calculator tells me I'm done because it hasn't done math, it's done an operation for me. But now I can come in and I can do f of 3, I can do f of 4, and I can evaluate those functions very easily just by entering them into the keypad. So now that I have this function, what I want to do is look at a way of displaying the data quickly on the Nspire. So I'm going to add a page, Control Doc to add a page. You can see it right there above Doc. And I'm going to put in a list in spreadsheet number 4. And what I'm going to do in this first column, you can see this is just a spreadsheet very much like Excel. I'm going to put some of those values from my table, 6, 10, 15, 30, 45, 180, okay? And so these are the number of sides that I have. So I'm going to go up in the first row, and in the box over this column, I'm going to type sides. And that will then define this column, all the data in this column, as a list called sides. Then I'm going to go over into column B, and in the equals row, this second row, I'm going to put equals f of, and I want it f of my variable sides. So I'm going to press variable to get sides. I could just as easily type the word sides, but if I have something defined, I can choose it from the variable key, press enter, and it fills in those values. Now, if we'd had time, I'd have paused and said, well, what kind of behavior do we expect on this table? And because we're circumscribed, we expect these areas to be bigger than pi and decreasing towards that value. And now I'm going to give this column a title as well. I'm going to call that area, press enter. And I want to look graphically at what these are. And a way I can do that on the Nspire is to press Control Doc. And I'm going to add the data and statistics page, this time number 5. And there's my data. It's all kind of like randomly spaced. Well, I'm going to come down here where it says click to add a variable. And my independent variable, my input was sides. It arranges my data in terms of those values. And then I'm going to click here and click area for the other column. And we can see this decreasing behavior. And if we had more values, if we put all the values in the table, we could get that same look that we had except we're getting a scatter plot here of those values. So before I finish, once students have done the inscribed, once students have done the circumscribed, I like to bring them together, and here is a picture of what they might see, where here's the area on the outer piece, here's the area on the inner piece, and what's happening is they're closing in on the area of that circle. It's like the graphs here are squeezing in onto that value of pi. If we go back to that area of polygon document that I have and click 3.1, here's that image. Here's the circumscribed and the inscribed, and as I increase those values, it's squeezing in on that circle, all in hopes that my students will get a hint of the squeeze theorem so that when I come back to it and we're doing it in a more abstract concept of limits, they'll have an idea that I can point to. And so what we're going to do now is we're going to transition, and Tony's going to talk to you more about limits. So let me give Tony control. You ready, Tony?
All right. I think so. I think we're sharing here. And it's funny, if you remember what Michael was saying, it's hard to believe that in less than 11 hours, I'm going to be standing in front of students for the first time since May. But I tell you what, watching Dennis, and I've always been a fan of his activities, it certainly got me a little bit fired up in kind of a tumultuous time. So I really appreciate Dennis for what he's showing and some other things he's got in store for you later this evening. But if you're watching the webinar, it's very likely that you probably are a calculus teacher, or maybe that you soon might one day want to become a calculus teacher, whether it's advanced placement or dual credit. And if you teach calculus, it's very likely that you are going to be teaching limits. And you're probably going to do that fairly early. It is Unit 1 in the new course and exam description. And what I wanted to do is focus primarily on, I guess, what we would consider to be topic 1.5 in the CED. It's entitled Determining Limits Using Algebraic Properties of Limits. And I've always felt that this topic has sort of a twofold sort of personality to it. Some of the more basic limits, our students tend to not have a lot of trouble. They absolutely crush it. It's the low-hanging fruit on the tree, and they seem to do a very good job. But it doesn't take a whole lot of manipulation to that particular limit question, that function, that composition, that product, to change it into what's sometimes called a tricky limit, or as one of my colleagues on the West Coast calls, a wicked limit that I'll be sharing with you in a little bit. So it's very likely that you all are somewhat familiar with these 5 properties of limits. And when f of x and g of x are fairly well behaved, we don't have much problem. So case in point, we take a look at a pair of graphs here. We've got a graph of f of x that certainly would be characterized by some kind of a piecewise function, and likewise g of x is the same. Now, if we want to find the limit as x approaches 1 of f of x plus g of x, sometimes our students sort of cross their fingers and sort of hope that things manipulate nicely, and it turns out that that's going to be the case here. Because we know that the limit of the sum is going to be the sum of the limits, and we can just approach 1 from both sides simultaneously as long as we have these nice, well-behaved functions. And in this case, the limit of f of x as x approaches 1 does certainly give us a value of 2. And the limit over here of g of x as x approaches 1 gives us that value of 1. And of course, 2 plus 1 is 3. So our kids are just thinking, wow, I've got this. Limits are easy. To maybe a problem that involves a quotient, we got to be a little bit careful about the limit of a quotient and making sure that the denominator is not going to turn out to be a 0. And I don't believe that that happened here, because the limit of the numerator, I believe in this case, is going to be this value 0. And of course, the limit of the f of x as x approaches 3 is going to be negative 2 over here. And so, of course, 0 divided by negative 2 is 0. So our students have this wonderful confidence, right? But then all of a sudden, things might start to change. And one particular way that things change is the introduction of the composite function. So let's say in this particular problem, we're defining this composite function f of g of x. And I'll just go ahead and kind of denote that here. We have f of g of x. So we have been told that if the limit of that inner function as x approaches some arbitrary constant does exist and it produces this result of k, and it's very important that these are events that both have to simultaneously be true, if that outer function happens to be continuous at the result of that limit for the inner function, then all systems are go. We can evaluate this limit of the composite function by, to borrow a phrase from our good friend Steve Kokoska, by pushing that limit through the outer function and letting it take hold of this inner function, and then computing our value of f accordingly. Now, while useful, this rule can sometimes be misinterpreted. If, let's say, we look at its converse, which is essentially negating both the hypotenuse and the conclusion, we feel like, well, if this limit, let's say it does produce some finite result k, but maybe the function's not continuous. It's so easy for us to think, well, this thing absolutely falls apart. We cannot use it. We're going to probably get an answer of does not exist. But that's not altogether true. What it means is that we really have to dive in a little bit deeper to really what does it take to find this limit. And it's all sort of centered around the idea of approaching the value of a from both sides. So we're going to see an example here and then try to use a little graphing calculator technology. I want to give a shout out to a few people. I'm going to go ahead and first of all recognize our friend Mark Crowley. Mark is a teacher from Denton, Texas, who's also a longtime AP question leader and just recently was an exam leader for the 2020 reading. And Mark had put together these graphs, and I've manipulated a little bit for an activity in my particular classroom. But I wanted to first of all kind of give a little scaffolding as to kind of motivate us, well, why are these composite functions important for us to teach and present them in our classroom? And it just seems like there's been a little bit of a paper trail from the 2016 practice exam and, of course, the international exam from 2016. And here's an AB version of the international, the IPE from 2017. So problems like this are showing up in those multiple choice questions. They're oftentimes very troublesome for students. And we can look at this from a couple of different standpoints. Yes, they're difficult. Our students are going to have a little bit of trouble with these. They're not the low-hanging fruit. However, I really feel by talking about these more complicated, tricky, or wicked limits, our students gain a better understanding of the idea of the limit in general. And they really start to focus on that idea of the fact that a limit is not about destination. A limit is more about the journey. And in this particular case, that journey is going to require us to approach from both sides. So if we go ahead and take a look here at our example 2, we're only going to be using the graphs of f of x and g of x for this particular session tonight. I have many other problems that do focus on the more complicated graph of h and this guy over here, J, and I'll show you where you can find a lot of these activities at the end of my presentation here. So for part A, we're going to be focused on finding the limit of f of g of x as x approaches 3. Well, according to what we saw on the previous page, this should be equal to, and how about I preface it, it's possibly equal to what we get if we just push that limit through. So we'd have the function f evaluated at the limit as x approaches 3 of g of x. That's what we hope to have happen. So it looks like we're going to have to be concerned with this limit of g of x as x approaches 3. That's something that we're very much interested in knowing. So we kind of think off to the side here. What is this limit of g of x as x approaches 3? Is that going to be tricky for our students to find? Well, look over here at the graph of g, and we see that, as we approach 3, really from both sides, we seem to nicely approach the value of 2. So I think we can feel very confident that that answer is 2. Now the question becomes, is that going to allow us to let this equal? And I'm questioning it, right? I don't want to put that equals there without the question mark because I know the chat may go crazy here. But I want to go ahead and think about the fact, is this f of 2? Because is that what a lot of our students might do? I think it's what I've seen my students do in the past. And if we think about, well, f of 2 is just equivalent to 3 in this case, and we feel like, wow, that could be my correct answer. Boy, what if this is a multiple choice problem and 3 is one of those distractor choices? And it turns out that it is not the correct answer. And the reason is because if we look at that function f of x, at x equal 2, we find that he is not continuous. Now, this might kind of come as a little bit of a surprise to many of you, because I mentioned that this particular concept could fit very nicely in topic 1.5 of the CED. And if you like to follow the CED from beginning to end, then it seems kind of confusing for students because continuity isn't really addressed until topic 1.11. But I don't think that that's a big problem, and I've done this for a few years with my own students, and I just basically give my students a very basic definition of continuity to begin with, and then we can build upon that in the upcoming sections as we move towards topic 111. So we don't have the continuity here at x equal 2, so what does that mean? Well, we have to think about the journey, not the destination. And how is it that we are approaching this 2? And we can see that we are approaching it from below, from the underside, from values that are less than 2, let's say. And the universal way to mention from below 2 is really 2 from the left, using that notation. So then what that allows us to do is, instead of thinking about this original limit, and I'm going to go ahead and just rewrite this. I'm going to try to be real formal. Math practice, right? Number 4, communication and notation here. So we're going to take this limit as x approaches 3 of f of g of x, and we're going to think of it as this. We're going to think of it as the limit as x approaches the limit of g of x as x approaches the 3. Now, I know for some that might be very kind of busy, let's say, and I know a lot of teachers like to use a substitution, like let u represent this entire limit statement, which is perfectly fine. But it turns out that I'm not going to linger here very long, because I've already computed that limit of g of x as x approaches 3, and I know it to be 2 from the right. So I've now transformed this limit statement into something that I think the students are going to be able to digest a little bit better, going to the graph of f, let x approach the 2 from the left side, and lo and behold, we see that the answer is indeed 1, which means I'm really embarrassed to even have this stuff up here, right? I don't even want that there, because that is the misconception that students can sometimes encounter. Well, this is a Texas Instrument Calculator webinar, so why don't we take a look at some technology that we can use to maybe reinforce this idea a little bit. And I will use both the TI-Nspire and the 84 this evening. I'm going to start with the Nspire for this particular problem, and I've just simply rendered that particular graph of f of x. So if you remember, I know I'm going to kind of go back and forth here. I want you to get a good look at this f of x and g of x here, because you're going to see those rendered on the graphing calculator. And fortunately, these aren't too terribly difficult to find equations for. You can see why I may have strayed away from giving an example with the j of x this evening. So we have our graph of f of x, and you'll notice I did a couple of things here. I decided to use obviously a piecewise function approach. You can find that just by going to the math template and using either of these two options. The option that's highlighted will always give you a 2-piece piecewise function, and the option to its right can give you 3 or more. And I decided to also define it as f of x. Some of you who are very experienced with using the TI-Nspire may have thought to expect an f1 of x here. Sometimes when I demonstrate a graph to my students through the TI-Nspire software, I like to use the exact name of the graph so that they won't get very confused. So I just deleted that one, typed it in as f of x. The Nspire has no problem with it, other than the fact that I think it might default to a light blue color, but you can change that very easily. I wouldn't worry a whole lot about these two. I always have people that ask about how to get these particular open circles and closed circles. It's really just a matter of making sure that, number one, you're in a document and not in a scratch pad, and then you can use the geometry feature in the menu in order to place points on your graph, and then from there you can change their attributes to be open or closed and change their size. But to be honest, if you were doing this on the fly, you wouldn't have to necessarily define those as open or closed, because limits are about the journey, not the destination, and we're still going to see our result being what it's going to be regardless. So here's our page 1.2. You can see I've done the same thing with the g of x function. Notice it is an absolute value graph. It seems to be a little upside down, so that's why we have the negative there in front of it. Now what I'm going to do here is, for page 1.3, I'd like to take a look at what the limit was of that very first problem, which I believe was f of g of x. So I can just hit this tab button and I can pull up the graph entry line, and notice the calculator remembers our good friends f and g, and I can hit enter, and there it happens to be the graph of f of g of x. And if you recall, and if you're like me, my short-term memory fades, I want to look back at this limit and remember what we were looking at as x approaches 3, but I don't think it really matters, does it? Because no matter what value x approaches, it seems like we're always going to have that y value of -1, and that turns out to be the result. Now, it might be worth mentioning that when students investigate this, they might consider, well, is that really the graph of f of g? Is that telling us the complete truth? Well, if we were to bring up the table, Control T does a great job of that, we can see that there is a little anomaly going on at x equals 3. So I suppose that we would have this removable discontinuity, a hole in the graph at the point 3, -1, and then the point 3, would be located somewhere above this curve. But that's really nothing to worry about, because you're probably tired of hearing it. We're about the journey and not the destination. And we're just focused about these values approaching 3 and staying at the y value of -1. Now, in part B of this problem, which I'm just going to briefly talk about, you can see I've already had the solution. I thought about changing the graph of g of x ever so slightly. So you can see this graph of g of x is now sort of uprighted. So we have this new version, and the way that that would affect the problem is that our limit of the inner function is now going to approach 2 from the right side. And so therefore, you can see down in the graph of f of x, I've just copied it and pasted here for your convenience. As x approaches 2 from the right, we would get a positive value of 3. It could be worth mentioning that which of these problems would you like to present to your students? Maybe if we presented part B of this example prior to part A, it might throw the students for a loop, and they might wonder, is there any difference in part A? But sometimes it's nice to kind of make these variations and just see what your students are thinking. If I move to this next slide, this sort of now takes it up a notch, right? We're now in certainly a group of limits that are going to cause us to have to think a little bit more. And we have a new pair of graphs here. And I want to thank a teacher from San Jose, California, Michael Batista, for putting these graphs together. And I've kind of run with it a little bit and decided to add some Nspire flavor to it and some TI-84 flavor to it as well. But if we look at part A, we want to find the limit now as x approaches -1 of f times g. So if we were just to kind of briefly go through these particular steps, our thought process as a student might very well be to begin by just taking the limit of the product, right? The limit of a product is the product of the limit. And so if we take the limit of f of x, as x approaches -1, we get, oh, right off the bat, does not exist. Okay, well, let's move on to the other part. What's the limit of g of x as x approaches -1? And we find that that's going to be 0. Okay, now the problem is our students probably don't know their multiplication tables for does not exist. What is does not exist times 0? We probably don't know what that means. But if we were to investigate this a little bit deeper, doing really what limits are designed to do, and that's to have us approach our target from both sides, we can see as we approach the -1 from the left, the f function certainly is going to give us a +1, and the g function is going to give us a 0 right here where the arrow is. So we have a result of 0. If we do the same thing, approaching -1 from the right, we end up with -1, as you can see indicated by the arrow, again times that same 0. And because the two results are 0, we can safely proclaim that the overall limit was going to be equal to 0. And you can demonstrate this just as easily whether you use the TI-Nspire or the TI-84. For example, the Nspire might look a little something like this. If I back up, I've got a sketch of f of x. Now, it was a little bit more challenging maybe to come up with these piecewise functions. How important is that, say, for students on the AP exam? I don't think it's very important. And I don't mean for these graphs to necessarily be proof of why these limit rules work, but I think they give the students that visual justification. We talked about connecting representations here as mathematical practice too. And so students certainly won't question that the answer is what it is when they can see that graphical approach. And then here's the graph for the g of x function that we saw on that previous page. And I'll flip back so that you can kind of lock those in your memory. And then, of course, we could manipulate very easily by going into another page where I just simply multiply the f times the g. And if you remember, our limit was allowing x to approach -1, and I believe the answer was indeed 0. And we see that that is the result here. Now, let's take a look at this from the TI-84 standpoint that does just as great a job. I have gone ahead and already typed in the equations for those piecewise functions into the y1 and the y2. It takes a little while to type in 4 pieces and 3 pieces, so I wanted to do that ahead of time. But I also wanted to make sure that those of you who might be holding on to a slightly older model of the TI-84 Plus that may not have undergone one of the latest operating systems is that in the math menu, if you either scroll all the way down to an option that doesn't show up on the screen, that maybe some of us aren't real sure that's there, but option B, we have this piecewise option. And of course, you can get there a lot faster if you were to scroll straight up. So option B. And then if you select piecewise, it allows you to decide how many pieces you want and select OK. And then it's very intuitive. You would just plug this in the way that you would see it right off the page. You could say, OK, my first piece would say it's X, and then you can use, say, -1. And if you need a inequality symbol, second math will bring up the inequality symbols, and you're off and running. Now, I know that there's a lot of people in the chat talking about, well, what is this operating system? Perhaps it's something that we can talk about, but it's something that you can get for free. You just have to use the TI Connect free software program that you can get from the Texas Instrument website, and a USB to mini USB cable that you likely have hanging around your classroom. And from there, you can just input the new operating system into your potentially older TI-84. Not all of the TI-84s will accept this upgrade if you have one of the first lines of TI-84 calculator models that came out, but the larger percentage of the models of TI-84 will certainly take that operating system up. So what I want to do is just get rid of this and then just show you, well, how would you, let's say, do this problem part A, this f times g? Well, we could just multiply these two functions together, y1 times y2. And we can do that very simply by going into alpha trace. That will bring up our function entry menu. And I don't believe that you need a multiplication. It is implied. So let's live life a little dangerously and not put a multiplication there. Alpha trace y2, and then this will give us the product of those two. And let's see what's going on in the graph. Notice I've changed these two to be dashed just so that they wouldn't basically occupy so much of the screen where it would distract us from what the actual limit would be with the multiplication. And we can see everything really does look just like it had appeared on the TI-Nspire. You can see that this product of those two limits, which does give you the limit of 0 when x approaches 1, is certainly in line with this graph that you see from the TI-Nspire. And of course, I could demonstrate the same things with the future parts of this problem. Part B is a difference. And I certainly invite you to take a look at any of the documentation associated with tonight's session. And I'm also going to share some other materials that you're more than welcome to use. And then in part C, we have this wonderful composite function, g of f of x, that will illustrate the same ideas. One of the things that I really like about these couple of problems is Michael Batista, who I just mentioned, recently created a wonderful video that you can all find on YouTube. And I believe Dennis might put this into the chat. It's just a bit.ly link here. And I definitely plan on showing this to the students because it'll walk through those 3 examples. It doesn't use TI technology, so you could certainly scaffold it nicely by using either the TI-84 or the Nspire, but it's a wonderfully presented PowerPoint that has a lot of great animations. It's really going to capture your students' attention. So Michael did a fantastic job with that. And then the other thing I wanted to share with you is I have a Dropbox just full of hundreds of resources. I recently aligned my curriculum with the CED, and you get to see a little bit of a snippet of what it would look like in its main folder, where I have some fun activities. Well, we hope that they're fun, right? And then I have all of the units listed, and within a unit, you can see that it's further subdivided into a few other folders. I'm going to add some other folders that have graphing calculator intervention, no matter what TI model that you might be using. And you can open up any of these folders, and you're welcome to use any of those activities that you want. A real quick preview of what one of the guided practice would look like. Here's just the Word file. Notice they're going to be in Word and PDF, so you could take this high school name off of it. You could put your own high school name. You could take my name off of it, put your own name. Say that you wrote it. Doesn't bother me. And you can just manipulate this and change it to any way that you feel that would better serve your students. I will admit that I do have the TI-Nspire focus quite a bit into this material, but it's not difficult to change this to a TI-84, perhaps a TI-89 interface, where you can take screenshots of those particular screens and embed it into your notes. But you're going to see that there's just every single topic is represented, and I'm going to scroll just to 1.5 real quick before I turn this off to show you exactly what it is that we spoke about this evening, and here it is. Here's that 1.5. Using the algebraic properties of limits, and you'll see some of the same problems here. So you're welcome to use that in its entirety, in pieces, to just supplement whatever curriculum that you're currently using. I want to, in the next couple of minutes, I want to make sure that Dennis gets a chance to talk about something else, because he's got a very neat representation with I believe, velocity. So Dennis, I'm going to assign you some control here and let you take over.
Okay, I'll try to do this briefly. I want to respect your time. We wanted to get to an activity on motion, and what I do is a unit 0 before we get into unit 1 with limits, because I want the students to have an idea of what they'll be entering in that year, and I think it's a good use of time for my students to have an idea of what the definite integral and the derivative are before we even get into limits. And so this is an activity that's available in the materials that you'll have, and there is a corresponding files for the 84 that you can do with this. And so what I'm going to do real quick is I'm just going to go to my 84 and press second program for the draw menu. I'm going to move over to the store menu and choose number 4 for recall a graphical database 1. And this graphical database is in the files that you have. But when I press graph, what I'm getting is the position graph that's in the activity graphed along beside this little dot that's moving, so that you can watch and be able to describe the motion. And so the big thing I really want for my students in this unit is that they learn the mathematical practices, they learn to communicate, but also that they can make connections to the concepts in their mind before we start to explore the more rigorous idea behind it. And you can see the same thing is available for you in the Nspire, and you can do that. So I just encourage you to consider teaching a little bit of calculus before you get into the nuts and bolts. I feel it's like, I don't know if you ever watched Willy Wonka, but there's a scene where they go into the candy shop and they buy the candy before they ever go into the factory. And if the kid can taste the candy a little bit before, it'll make the trip to the chocolate shop a whole lot more meaningful. So I just encourage you to take a look at this and see what you think. And I will give this back to Mike.
Thanks so much. To receive a certificate of attendance for tonight, go ahead and click the link in the chat window. Also listed is the important documents link from tonight from Dennis and Tony. If either of those links aren't working for you right this second, don't worry, you'll automatically get a follow-up email within a couple days, and that follow-up email will contain links to the certificate, the documents, and the recording as well, so you can go back and watch this at your own pace. Lastly, if you are watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. Thanks so much, Tony and Dennis, for everything you shared tonight. It definitely is getting me excited about my first day of teaching calculus this year, which is coming up pretty soon.
Oh, welcome, Mike. It's been great to be here and to share.
Oh, definitely. Thank you so much, and just such a fun evening. I always love talking to passionate math teachers about mathematics and in particular calculus. And Dennis and I both wish everyone a great and particularly a very healthy school year.
Yeah, I second that. Thanks everyone for joining us. We hope you stay safe, and we'll see you back online real soon. Have a great night.